Students, our today's lecture will focus on the crystallographic points, direction, and planes. Or essentially, we will talk about how to quantitatively describe a crystal structure. We will first start from point coordinates. So how to describe a point position in a crystal structure. So, for example, if you have a unit cell characterized by this, A, B, and C, which are unit cell edge lengths. And if we want to write down the position or the coordinate position of this P position, what you need to do is to write a vector from your origin O to P. So OP is this one. And then you decompose this OP vector into the directions of your unit cell edges. So essentially, if you write down the OP vector as a combination of your unit cell lengths A, B, and C, and these indices, Q, R, and S, will be the indices of your position P. So essentially, this is a very quick practice. For example, if you want to know the position of your number 1 point, okay, so this is your number 1 point, which is essentially your origin, so that the indices are 0, 0, and 0. And if you want to know your number 2 point, so this is your number 2, and this one you can easily tell is that it is on the x-axis, and its length is identical to the edge length of your unit cell, so that your index of this position is 1, 0, 0. And if you want to know, for example, the coordinate of your position 5, then you can write down the vector between your origin number 1 to your number 5 position as this one, and you can easily tell that the indices corresponding to this position is 1 over half, 1 over 2, 1 over 2. So that's point coordinates. And second, we will going to see how to describe quantitatively the crystallographic directions. So the direction in a crystal structure is by definition a line between 2 points, which is a vector. And there are several guidelines or principles on how you can describe these crystallographic directions. So the first one is any direction parallel to each other are equivalent and should have the same indices. And you should indicate the special directions in a crystal by this squares, UVW, which the UVW are the indices corresponding to the direction. So for example, this is the way you describe or you determine the particular direction in the crystal structure. First, it has to pass through the origin of the coordination system. Second, the length of the vector projection on each of the 3 axes is determined. And then these 3 numbers are transformed to the smallest integer values. And the 3 indices should be closed in a square bracket. So that's the sequence, how you determine a certain direction in a crystal structure. So for example, a quick practice is this. Write down the direction indicated by the green arrow here. So you write down the direction of this vector here, right? So you follow the sequence, right? So its projection on the x-axis is 1 over 2, right? And its projection on the y-axis is essentially 1. And it has no projection on the z-axis, so this one would be 0. And then you reduce these indices into the smallest integer number, so you have this one, right? So this is your indices for this direction. And for your practice, please draw these directions for your homework. And another important concept is the family of crystallographic directions. And you will know that there are several non-parallel directions with different indices are so-called crystallographic equivalent. For example, you may have 4 111 typed non-parallel directions in a cubic cell. So these are the 4 non-parallel 111 directions. And all of them are the so-called crystallographic equivalent. And they can be considered into a single family of crystallographic directions. And then you change your square bracket to a so-called angle bracket. So you write down your 111 direction groups like this. And in a similar way, you may have a number of equivalent 110 directions. And then you just write down your 110 direction group as this one. And caution has to be executed when the lattice is not cubic. The point is that in cubic lattices, the x, y, z axis, they are all equivalent. So that 111 is, or 110 is equivalent to 011. However, for non-cubic lattices, these small directions are not necessarily equivalent. So you have to use this norm with caution. Now we move on to describe quantitatively how to define a crystallographic plane. Okay? So essentially, you need to follow this sequence to determine the indices for the planes. And this principle is developed by this scientist called Miller, and the indices for the crystallographic planes are also called Miller indices. So first, the plane, if the plane passes the origin, then construct a parallel plane that doesn't pass the origin or select a new origin. So this is the step 1. Essentially, it means that your plane shouldn't pass the origin. And second, find the intercepts of the plane along the axis x, y, z in the unit cell. And third, take the reciprocals of the intercepts and then convert into the smallest integers in the same ratio. And finally, enclose the parenthesis UVW. And UVW will be your indices for your crystallographic planes. Here, for example, you have these 111 type planes, right? So the intercept between this plane to your x, y, z axis is actually 1, 1, 1. And you take the reciprocals are still 1, 1, 1. And then you can finally give the indices for the crystallographic plane as 1, 1, 1 plane, right? So in a similar way, you can also evaluate the crystal orientation of these planes, and you can easily tell that in these planes, they are 110 typed planes. So here is a relatively more complex example. You are asked to determine the indices of this plane, right? And this plane is passing through the origin O, right? So remember our step 1, whenever a plane is passing through the origin, you either have to define a new origin or move the plane to a parallel position. And here the solution is that you define a new position or new origin like here, which is called O prime, okay, O prime. And then you just determine the indices of this plane in this new coordinate with the origin of O prime. And then by definition, you need to find the intercept of this plane with the x, y, z axis. So essentially, because this plane is in parallel with your x-axis, right? Your x-axis is here, so it's in parallel with your x-axis. So the intercept would be infinity. And secondly, find your intercept of this plane with your y-axis, right? It is -1. Right? And then the intercept of this plane with the z-axis is 1/2, right? It's this one, 1/2. And then you take reciprocals, you can find the indices of this. Okay, so that's the indices of your plane. Okay? So similar to the crystallographic direction groups, you may also define the family of crystallographic planes. So this 100 plane, 001 plane, and 010 plane, they are all equivalent. You can easily imagine. And then you just use this sign instead of your parenthesis. So your parenthesis for particular crystallographic planes is converted or is changed to this braces whenever you talk about the crystallographic plane groups or plane families. And again, caution has to be executed when the lattice is not cubic, because for non-cubic lattices you may have difference, or the XYZ directions, they are not necessarily equivalent. So, and here I just show the example of a family of 110 planes. So these are the remaining 3 110 typed planes. Now we move on to talk about the crystal structure and its quantitative description of hexagonal crystals. So because it has a hexagonal symmetry, so essentially instead of using a 3-index system, you are going to use the 4-index system of A1, A2, A3, and C. Okay? So you have a so-called basal plane. So the A1, A2, A3, they are forming this basal plane. And all the side planes are called prism planes. Okay? And in practice, the C over A ratio is varying for different structures. And for HCP structures, it is 1.633. Okay? So this is just for your practice. So you can, in a similar way with cubic lattices, with the A1, A2, A3, and C axis, you can describe quantitatively the particular crystallographic planes and directions. Now we are going to discuss two important concepts of linear atomic density and planar atomic density. So sometimes you want to know how dense the items are packed in certain crystallographic directions and planes. And linear density of items are defined by definition. It's the number of items centered on the direction vector divided by the length of the direction vector. And the planar density of items is the number of items centered on the plane divided by the area of the plane. So these are actually important factors when you consider which direction and which plane are having denser items packing than the rest. So that's also important for a lot of properties of crystals. You will see more and more of the consequences of this linear density and planar density of items in certain crystallographic orientations in the future lectures. So finally, we are going to talk a little bit about the packing sequence in FCC and HCP structures. So for a closely packed structure, so when you have A items packing very closely to each other, so all the items are touching each other in a sense. So essentially you will have two types of packing sequence on top of or in the bottom of these A items, which are actually this C position and this B position. Once items are fully occupying these B positions, no items can occupy these C positions anymore. So essentially you will have two different combinations of closely packed structures. And one actually is FCC structure, the other one is the HCP structure. In particular, if the neighboring atomic planes are packed in the AB, AB, AB sequence, then the closely packed structure will be called hexagonal closely packed or HCP structure. And alternatively, when the neighboring atomic planes are closely packed by this BAC, BACs or ABC, ABC sequence, it will give this FCC structure. So essentially you will have two most closely packed structures of HCP, and FCC. And then now you understand why your atomic packing factor for these two structures are both 74%. So essentially it is equivalent or equivalently atomic closely packed structures. And here I just show an example of FCC structure seen from the 1-on-1 directions. So for today's lecture, we have talked about the quantitative description of crystal structures. Thank you very much.